Okay, so all these support vectors will be, as you said, it is you say unit distance away from the uh, classification boundary. Okay, shall we go ahead? Yes.
Yes, sir.
Yeah. So these are the terms that we have introduced. So this could be a hyperplane rather than the line, and this we have discussed because when we have multiple features, okay, I mean if it is univariate system, then it is line. Like if I write it as theta 0 plus theta 1 x, this is a line. But if I add one more feature, let's say theta 2 x, this is x1 x2, okay, so then this becomes a plane rather than the line, and that's why this is called as hyperplane. So you have considering two features, x1 and x2. Let's say this is x1 and this is x2. So if I have two features, then my equation will be hyperplane. This is a margin, okay, and these are called as support vectors. So please remember this diagram. Yeah. So margins in case of SVM, we are keeping this margin as unit distance. So we are going to talk about. So how this mathematically written, and we know that in general form of this mathematical model, okay, this could be written as theta transpose x plus theta 0. We know that. For this is a bias, and for this is a dot product. Okay, so I have theta vector, theta 1, theta 2, and features or data points as x1 and x2. Okay, so this theta transpose x actually represents this theta 1 into x1, theta 2 into x2. It is as simple as that. Okay, so if I take a transpose of this and multiply with x, I get this equation back. So this is a general way to write the model. Okay, any model, be it linear model, be it non-linear model, but in machine learning model, this is a shortcut, you can say, or the proper way to mathematically write the equation for the model. So theta transpose x plus theta 0, this margin should be greater than or equal to 1. So at least margin should be 1. Okay. Now keeping more margin is also not useful because you are restricting uh, some of the regions, isn't it? So it has to be sufficient, not very high. And so, but that should not be less than 1. That is what this criteria says. And so for when y is equal to 1, that means when your class is target class in the given data, when it is y is equal to 1, so for all these plus samples, it should be greater than 1. And for dot samples, it should be less than minus 1. Okay, actually, this is coming as negative. This is going to come as negative, and that's why it should be actually less than or equal to minus 1. It is written as like this when y is equal to minus 1. And since y is equal to minus 1, this is going to be calculated as negative. Later on, I will show you. So in short, this can be written as y multiplied by this. So this is, so entire thing, these equations can be written as this. So it is y into theta transpose x plus theta 0 greater than or equal to 1. When y is equal to 1, you will have first condition. When y is equal to minus 1, you will have second condition. But the total margin, as you see, it is 1 to this side, this is minus 1 to this side, and total margin is actually of 2 units. Let's go further. So we have already talked about logistic regression function. So when it comes to support vector machines, SVM, how do I write the regression, logistic regression function, or this is error function? This is error function, or we call it as cost function in SVM. Please remember the equation, okay? There could be questions based on this and based on this shape, and try to understand how this actually becomes a convex, okay? Now this is literally not exactly convex, and let us see how you get this function modified. So in general, we have seen that in logistic regression is another name for classification. We have already studied this. Okay. So for classification or for logistic regression, what should be my error function or cost function? It is in general written as log likelihood, y into log of y cap plus 1 minus y log of 1 minus y cap. Okay. So this comes as, or this could be written y cap could, the problem y cap can be written as h theta x comma y, or simply h theta of x. Okay, so these are different styles, these are different ways to write the uh, function, okay, which we write it as a mathematical model for the given problem. Okay, so either we write in the form of y cap is equal to f of x or something like that, or we can write this as y of theta. Theta are the weights, and theta x, or simply y of x or y of theta. Okay, some people use h as a function also. So don't get carried away with the different notations, and that's why I have written in blue that this is nothing but this function, and this is already we have seen minus y into log of y cap minus 1 minus y into log of 1 minus y cap. What is this term, last term? Can anybody tell me what is the last term?
That's a regularization term.
Yes, exactly. So this is a regularization term, and that we have introduced for regularization. It is lambda by 2, okay, m number of samples, and we are actually taking a norm. It is L2 norm of all the weights. Okay, it is L2 norm of all the weights. So this is a regularization term. So during practicals, when we actually do the program, uh, I will show you how to regularize the model, how overfitted model can be controlled. Okay, and it's a very simple thing that when it comes to Python. Okay, so let us not worry about it. So try to understand that when y is equal to 0, okay, that means we are, this is a target class. When y is equal to 0, if I substitute 0 in this equation, I will get this term cancelled and I will get this term present. So if I put y is equal to 0 in this equation, I will get minus into log of this 1 minus y cap. And y cap, you know that it is 1 upon 1 plus e raised to minus theta x. Actually, there should be there should not be only x, but that is theta x. Okay, assuming that theta is equal to 1, then I can write, just to simplify this equation, it is 1 upon e raised to minus x. What is this function? This already we have seen. Yes, quickly. Yes, anyone? 1 upon 1 plus e
Sig-
raised to minus. Yeah,
sigmoid function.
correct. So this is sigmoid function. Please don't forget. And sigmoid is very much essential for the classification objective logistic regression. Okay, so don't forget that this is a sigmoid function. So now you can look at here. If my x is equal to 0, x is equal to 0, what will happen here? X is equal to 0, e raised to 0 is 1, so this is zero point 0.5, this is 1 minus zero point 0.5, this is log of zero point 0.5. So log of zero point 0.5 comes to around zero point 0.3, minus zero point 0.3, minus zero point 0.3 minus, this will become plus, and somewhere at 0, you will get the value here around zero point 0.3, okay, around zero point 0.3. It is slightly less than zero point 0.5, okay. But when x is equal to minus 1, this is our margin. This is 0, this is a margin. So margin is minus 1 when y is equal to 0. This is what we have seen in the previous slide. So when we put minus 1 here, this term gets reduced to 0. So any value greater than this minus 1, or rather less than this minus 1. So if I put x is equal to minus 2, again the value will be 0, and so and so forth. So if you look at the how it will put the function, logistic function, when y is equal to 0, it is like this, red. But as you see here, this is the margin introduced. This is the margin introduced. So at 0, my classifier output is not becoming 0. Okay. So it is waiting till minus 1 to other side. Okay. So till minus 1, it is giving me the same class, y is equal to 0. This is the meaning of this. Okay. So by mistake, if any sample lies in this margin, that will be taken